Alright, welcome. In this video, we're going to continue our discussion of rates of change. But today we're going to kind of step it up a level, and we're going to talk about when those rates are changing. So first we need to kind of have a definition of increasing and decreasing. And what you see on the screen here, what you see in your notes book, it's a little technical. But what we can take out of it is like that the average rates of change for an increasing function are always positive. And on the other side, that a function's decreasing where its rate of change is negative. But we'd already seen that kind of in the last lesson. Okay, so let's start with discussion of the graph of y equals x squared. So we're going to start by sketching the graph, and we've got a table down here that we'll get into that in a second. So I'm just going to sketch in the graph. You know what this looks like. And if we're asked on what intervals is f of x increasing, really go back to there. Increasing is where the average rates of change are always positive for any 2 points in that interval, or where the function has a positive slope. And so that's going to be where x is greater than 0. And that means that, when we're looking at a picture of a graph, the function's going to be increasing when, as we move left to right on the graph itself is going up. And then as far as decreasing, that would be when x is less than 0, because the average rates of change are all negative. So I would say that f is decreasing on the interval where x is less than 0. Now, if you want to write these as intervals, that's perfectly fine. I actually need you to be able to recognize both of these things, both of these notations equivalently, like in a multiple choice setting. If you wanted to make them closed intervals, that'd be fine too. That's not something we're really going to get into in AP Precalculus, the difference between open and closed as far as increase, decrease, any of this stuff. So don't worry about it. That's just like we're not gonna mess with you on that level. We have plenty of interesting questions we can ask without getting into those differences. All right, now we're going to look at the table of values for this function and compute the average rate of change of f on each subinterval. And just to remind you, this is one of the key things from the last video, the average rate of change of f on the interval a to b is going to be given by f of b minus f of a over b minus a. It's just rise over run, like we've done in other classes before. So if we go to do this, just say on the first interval from -4 to -3. Okay, what's going to happen is I'm going to take, all right, well, f of -3 minus f of -4 over -3 minus -4. And that's going to be 9 minus 16 is, oh goodness, that's going to be -7, and then we're going to divide by -3 minus -4, which is +1, and so I'm going to see that the average rate of change was -7. But then you'll realize, all of these x intervals are spaced out by 1, so we're just really looking at the difference in these two. So that went down by 7. You don't need to sit there and watch me do the arithmetic, so I filled in the rest of those for you. And what we'll see is, how are the rates of change changing? And I guess there's a couple of things I'd say. First of all, we saw in the last lesson that the average rates of change are going to form a linear pattern, and that's true. Each time the average rates of change are getting increased by 2. But I think the important thing here is that we're noticing that the average rates of change, those numbers in black, they are increasing as x increases. They're going from -7 to +7, which is certainly an increase. All right, now we're going to look at this function g, which is another quadratic function, and it opens downward, and we've got a graph and a table of values right there. When it says analyze the rates of change of g, I don't exactly remember what I was thinking when I wrote this, but I don't think I meant for us to go in and compute the average rates of change again and do the exact same thing. I think what I was envisioning was for us to look at the picture of this graph and say, well, x equals 2 is really where all the action's happening, where it changes from increasing to decreasing. And so I would say probably, I think what I meant to say is that the rates of change of g are going to be positive before x equals 2 and negative after x equals 2. And then, maybe I'll add a little extra note that they're positive when x is less than 2, and then they're negative when x is greater than 2. Right. How are the rates of change of g changing? Well, if they're going from positive to negative, that means they're decreasing. Now, if we asked where g itself was increasing and decreasing, that's where we're starting to get into the language thing. And I think that's going to be the most challenging aspect of these problems for you, is this like unpackaging or decoding the language of the question. Right, because we just said the rates of change are decreasing, but g is going to be decreasing in entirely different places. Okay, remember, g decreasing is where as we move left to right on the graph, we're moving downhill. Okay, so that's going to be over here, and that's where x is greater than 2. And we also said earlier that's where the rate of change is negative, so I'd say that happened over there. I was thinking, we've already kind of mentioned that earlier. Okay, now when is g of x increasing? Well, that's when its rate of change is positive, or on the graph, when as I move left to right, the graph is going uphill. So we're increasing, and then we stop increasing at x equals 2. So g is increasing when x is less than 2. And then the question, what is the maximum value of g? Okay, g is reaching its maximum up here at the top of the graph. And that's happening at the point 2 and 6. So to its question, okay, that's happening there. We know that if the point 2, 6 is on the graph of g, that means that g of 2 is equal to 6. But it asks for the value of g, so that's going to be the output value. That's going to be 6. And so maximum value of g is 6. Now, on the topic of maximum and minimum, I guess we're going to define that right here, and we're going to say that a maximum in this class is just going to be where f changes from increasing to decreasing, and a minimum will be a place where a function changes from decreasing to increasing. And I think, that's a little zoomed in for your view. One thing that you need to know is that oftentimes they're called relative maximum, relative minimum, but they can also be called local maximum and local minimum. By that, it's the exact same thing. All right, so a maximum, might look like that, kind of smooth, like the one we just looked at, but it could also happen at like a sharp corner. Okay, that doesn't mean it's not a maximum. It changed from increasing to decreasing at that point. Those are what we would call maxima. And in the same way, anytime the function went from decreasing to increasing, that would be a place where we were having a local minimum. So let's keep moving and work on this next example. So the figure below is showing a graph and a table of approximate values for h of x equals 1/8 of x to the third minus 2x. Okay, describe the rate of change of h. All right, and I'm going to do the same thing I did before, and color the areas of increase in red and the areas of decrease in blue. Okay, so as I move left to the right, the graph is going up here. So this is what we would consider to be increasing. All through here, increasing, and then we reach a maximum. Okay, maximum being a place where we switch from increasing to decreasing. And then we decrease for a while, and then we increase again. And those relative extrema, the local maxima and local minima, those are places, where we're seeing a change in increase-decrease behavior. So what I would say is the rate of change of h, any place where it's increasing, is positive. The function decreases for a while, so that means that the rate of change would go negative. But then a while after that, somewhere between x equals 2 and x equals 3, we hit a minimum and we resume our increase. So that would be the rate of change going back to positive. Okay. So I'd say positive, then negative, then positive again. All right, so where is h increasing / decreasing? Right, well, h is going to be increasing where it has a positive rate of change, and I've colored it on the graph. Oh yes, but of course, we don't actually know the coordinates of these extrema, because in order to do that, we would need to be doing calculus, not precalculus. So I'm just going to call these points A and B. It's true that A is the negative of B, but again, to know that for sure, you would need, I think you would need calculus, or at least some sort of like a further analysis of the original function. All right, so from negative infinity up to A, the function's increasing. So let's say increasing when x is less than A. But also, after B, when x is greater than b, the function starts to increase again. So I'd say x is greater than a, also x is less than a, and x is greater than b. Okay. As far as decreasing, it's happening when x is between a and b. So let's say a is less than x, which is also less than b. And then describe how the rate of change of age changes. So I'm going to go back to two questions before, where it says describe the rate of change of age. I said it was positive, then it was negative, and then it was positive again. Okay. So let me just think about, no, I'm not going to do it like that. Think about a number that was positive, and then it became negative. Okay, that means it had to decrease. But then when the rate of change goes back from negative to positive, that's going to be an increase. So it's going to be that the rate of change decreases, and then it increases. This is, a lot of language here, and I think that we need some better terminology to help us, clearly look at these things. So that's where we're going to get into the concavity vocabulary. Okay? So we're going to say that the graph of a function f of x is concave down when the rate of change of f is decreasing, and concave up when the rate of change of f is increasing. Okay, and I'm just going to show you a picture of concave down and concave up. Okay, there it is. Really, that's what I'm going to want you to think in this class when we think about concave down and concave up, is the attitude of the function. Is the graph happy or is it sad? Is it smiling or is it frowning? Now I'm going to jump in and show you what that has to do with rate of change increasing versus decreasing, but really I think that's the first and most important thing I want to say about concavity is that concave up is where the graph of a function is smiling, and concave down is where the graph of a function is frowning. So concave up is smiling. And we're saying that's where the rate of change increases. And so the rate of change really, it gives us the slope between 2 points. And this is just like a very, very rudimentary drawing. But if we had a rate that was increasing, well, the slope would get steeper, right? Because the rate is the slope. Okay, and so what we would see is something like that. We don't really work with too many functions that look like just multiple pieces of lines smushed together, so it might be more curved, and that's where we'd see that smiling attitude. Now, I think it's important for me to also mention that a function doesn't necessarily have to be increasing to be concave up, right? That this is going to be concave up as well, because look, I put eyes on top of it, it's smiling. Okay, but the reason here is that, the rate of change is like the slope. And so if I looked at the slope right here, that's pretty negative. But over here it's less negative, and over here it's pretty close to 0. And so if you think about something that's negative and getting closer to 0, that is increasing. Right? And similarly for concave down, where the function's graph is frowning, think about the average rate of change decreasing. That's what we said was happening. The rate of change decreased. Okay, so the slope between these points was decreasing. So in a straight line case, it would look like that, which already is, not that happiest look ever. But I think if we were to draw in a smooth curve here, we can see that's definitely a frowning face, right? And again, doesn't have to be increasing to be concave down. It could be happening there as well, okay? Because the slopes could be negative and getting more negative, which would be decreasing. All right, so back to our example, we're going to determine the intervals on which the graph of h is concave up and concave down. So we're going to go back up to here to the graph. I'm going to actually erase the blue and the red. I will leave the a and the b. Why not? But we're going to be looking for intervals on which the graph is happy and sad, really. So I'm going to go over here and I'm going to say, all right, well, I can see pretty clearly here, this is a smiling face. Okay. I can think, we don't really have the tools to determine exactly where the point, where the concavity or the concave upness ends. I'll talk about that in a second. But, we're just going to go best we can tell, and it looks to me like it's probably here at 0. So I'm going to say, all right, this all looks like a smiling face to me. So the rates of change are increasing. This is going to be concave up through here. So that's where x is greater than 0. So concave up, that would be x is greater than 0. And as far as where we're looking for, the graph frowning over here, well, that would be over here to the left of x equals 0. So that's where x is less than 0. Draw the face in there like that, but you can see it's not happy. So we're gonna say concave down, that's where x was less than 0 on that particular graph. All right, now point of inflection is just gonna be a place where the concavity changes, where it changes from concave up to concave down, or from concave down to concave up. Okay, so they're saying the graph of y equals f of x is shown in the figure below. The graph of f has points of inflection at x equals 1 and x equals -1. Let me show you what I mean. So I labeled the points of inflection and then I kind of colored the areas around them. And notice how in the blue area, if I put the eyes up above the graph's smiling. Okay? Whereas, I don't know, that nose looked a little sinister. If I just leave it without a nose, it looks a little better. And in the middle, the graph is definitely frowning. Okay, so those yellow points are where the attitude of the function, the attitude of the graph is changing from positive to negative, right? Happy attitude to a sad attitude. That's really what we mean with these points of inflection. Okay, but this question here, I'm going to start off a little bit easier. Where is f greater than 0 and when is f less than 0? Now remember, f of x, that's like the y-coordinate on the graph, so we're just asking when is the y-coordinate positive and when is the y-coordinate negative. I just went in with a highlighter and separated this graph out into places where the graph is above the x-axis and below the x-axis, where y is positive and where y is negative. So I'm just going to kind of backtrack those to the x's that got me there. Say the function was positive, greater than 0, on the intervals -infinity to -3 because of the x's that generate a positive y value, and -1 to 1 and 3 to infinity as well. And so for negative, I'd say that would be between x equals -3 and x equals -1, and also between x equals 1 and x equals 3. Okay, now if we look and try to determine when the rate of change of f is positive versus negative, okay, I was trying to emphasize earlier on in this video that that's where we're looking at where the function is increasing and decreasing. Back to the graph, and we can kind of label it a little bit. We can say, all right, f is increasing when as I move left to right on the graph, I'm going uphill. Okay, so that'd be right through here, and then over here as well. Okay. So that would be between -2 and 0. And also when x is greater than +2. Okay. And if we're looking for where the rate of change of f is negative, that's where f is decreasing. Decode that and go to the graph, where as I move left to right, the graph is moving downhill. Okay, so that's where x is less than -2. And also between x equals 0 and x equals 2. So, whoops, I guess I'm going to say 0 is less than x, which is less than 2. All right, now when it asks us about concavity, when is f concave up, when is f concave down, we're just thinking about the attitude of the function. Wait, didn't it tell us? Okay, I think I must have already done that. I definitely already discussed that, but I will just point out that the graph of f is going to be concave up through here because the graph is smiling, concave down through here because the graph is frowning, and then concave up again because it resumes smiling. We knew that x equals 1 was where the attitude changed because they told us in the statement of the question that those were the points of inflection. Okay, now I'm just gonna leave that there. Alright, so let's keep moving. There's plenty of more examples for us to do here, and I'm trying to keep this video from being just super long, but this is an important topic, so we're gonna have to put in the work here. Alright, so next one. The graph of y equals g of x is shown in the figure below, points of inflection at 1, 3, and 4. Maybe I'll label those. X equals 1, x equals, 2, 3? Oh, I don't think that's quite right. I'll be honest, I don't just love this example in terms of what it has to offer that the other ones don't. I don't really think it has anything. And so I'm just going to keep moving to the next page. All right, I do like this one though. I like this one for your chance to try this on your own. So there's, well, let's just do these first 4, okay? Because then we're going to start to combine some stuff here. Try to figure out where the point of inflection, local maximum, local minimum are, and find any intervals on which f is both negative and decreasing. And do that with video pause because I'm just going to flash in the answers here in a second. All right, there you go. Best I can tell, f has a point of inflection at x equals 2. Kind of wanted it to be a whole number. Looks like it's about there, and it looks like to the left of x equals 2, the graph is smiling, and to the right it's frowning, so that would be where it had an attitude change. The maximum's happening at x equals 3, and the minimum's happening at x equals negative 1. Those of you that worked with an Algebra 2 last year, y'all were really good at identifying maxima and minima, so I'm not going to spend too much time on that. Negative and decreasing, we're looking for where the function is both negative, that's below the x-axis, and decreasing, so as I move left to right going downhill, so that's from negative 2 to negative 1, and from 5 to the edge of the graph, which is evidently 5.4. All right, positive and increasing, and all right, so here we start to like add things together at the same time. And so what I think I'm going to do is I'm going to come back to these in just a second, but after I move forward to the next page on page 19. Okay, so we're going to sketch a graph of a function that fits the description. And this is going to have like two things going on at the same time. Okay, so I'm going to just sketch them in real quick. Negative and increasing is like that, positive and decreasing like that, negative and decreasing there. We would need positive and increasing. I remember there was something off with this table. Positive and increasing would look like that. It doesn't have to look like that, but just in general, it's positive and increasing. It's above the x-axis and it's going up. Okay, increasing and concave up. Okay, remember increasing is going uphill and concave up is smiling. So I'm going to draw, I don't know, something like the right half of the graph of y equals x squared. I put eyes on top of it, it's smiling, and it's going uphill. Increasing while concave down. And so we are going up, but frowning. Okay, and that's actually a pretty good hint of how we should draw it. So I'm going to just, maybe something like that, like a graph of a square root function or a log function or something like that. Okay, decreasing and concave down is where we're going downhill and frowning. Okay, so that's going to be like, I don't know, negative x squared, the right half of it at least. But it didn't say anything about whether g was positive or negative, so that's why I'm drawing these crossing the x-axis, because nobody said anything about whether it needed to be positive or negative, so it could be both, it could be either, whatever you want. Okay, decreasing and concave up is going downhill while smiling, like the left half of that guy's smile there. So something like, 1 over x, or some kind of possibly related function. I don't know, it was going downhill and it was smiling. All right, now, increasing at a decreasing rate. These are particularly tricky, and I'm just gonna, I'm not gonna like try to psych you out or anything. I'm just gonna tell you, you should be careful with these. All right, and I think my advice to you is going to be when you're confronted with one of these where the language is a little bit tricky. What we should say is that the rate is decreasing. Okay, we take that out. Okay, g is increasing, you know what that means, it's going up. But if the rate is decreasing, that means concave down. I don't have a whole lot of room to write that, so I'll abbreviate it with concave down. And concave down means we're frowning. So we're increasing while concave down. And I know I just drew a picture of that, but I'm not going to rely on that, at least not right now. I'm going to say, all right, increasing while frowning would be, I don't know, something like that. G is increasing at an increasing rate. Okay, same idea. Decode increasing rate is going to mean concave up. Okay, and increasing while concave up, that's not happy eyes. Okay, let's say increasing while concave up, like y equals x squared, something like that. At least the right half of it. Okay, and g is decreasing at an increasing rate. Okay, decreasing, g is decreasing. We know that means our graph has to be going downhill. Increasing rate, just said, that's going to be concave up. So decreasing while happy. So something to that effect. And then decreasing at and decreasing rate. Oh, that's embarrassing. But those are the types of things we can fix. Decreasing rate, we're going to say, all right, if the rate is decreasing, that's what it means to be concave down. Okay, so decreasing while frowning is going to be that. Okay, so having all of these to work with, this could be a useful reference for us. I never did this one where it said positive and increasing, but I know y'all are pretty good at these. So positive and going uphill, that's going to be all of those values. So that would be from 0 to 3. So 0 is less than x, which is less than 3. Okay, but increasing and concave up. Okay, now if you want to just like flip back or flip forward to the next page, whatever, you can do that. But I'm going to just say increasing while smiling. That's going to be like that. So I'm looking for where the graph really looks like that little piece that I drew right there. I'm seeing it here. Okay, but then at that red dot, that's where we're switching concavity. That's where the attitude is changing. That's where it's going to switch from smiling to frowning. So I know that I need to be increasing while smiling. That's just going to be from -1 to +2. This is another one of those things where if you wanted to make it a closed interval by including -1 and 2, that would be totally fine. That's nobody's going to care either way. All right, increasing and concave down. So we're going up while frowning. Okay, so that'll look kind of like that. So I'll be looking for that on the graph. Where is that happening? Okay, let's get rid of that and go back and color in black right here. Okay, it's the only place where I'm seeing increase while frowning. Okay, it'll be right there. So that's just going to be 2 to 3. Okay, decreasing at an increasing rate. Okay, remember, increasing rate, we're going to translate that. Rate is increasing, that's concave up. Okay, so we're decreasing while smiling. So that'll be this shape here. And I bet we've got some of that. Do we? Yeah, it's right back here at the very beginning of the graph. It's part of what I've got highlighted in yellow, but I don't think I need that highlighter anymore. Okay, so I'm going to say that was happening down here. Decreasing while smiling, -2 to -1. Okay. Decreasing at an increasing rate. Is that not that? Hold on, that looks like the exact same thing. Pretty sure I meant to, do all 4 types, so it will do decreasing at a decreasing rate. So that's going to, F is decreasing. If the rate is decreasing, that's going to mean concave down. Okay, so we're decreasing while frowning. So that's going to look something like that. Okay, that's pretty decent sketch. All right, so decreasing while frowning, that's happening over at the far right edge. And that would make sense. It's kind of the only area I haven't colored on recently, and so that's where x is greater than 3. Or I could say 3 to 5.4. I forgot that this had a bit of a limited domain. All right, so the rate of change of f is increasing. We're going to translate that. If the rate is increasing, that's concave up. And we may have already done that. No, I did not find where it was just concave up in general. Okay, over there, that's where I'm looking for it to be smiling. Okay, I'm seeing that over here. That's going to be all the way from the start until the point of inflection. Okay, so that's when, from -2 to 2, or you could just say x is less than 2. All right. Okay, we already did these. We sketched the graphs of functions that fit those descriptions. All right, so the last thing we have to do here is kind of apply the same principles to some tables of values. So we're going to use the table of values to determine which statement about f could be true. And this is a very simplified situation here, but I think that this is all I need to show you. I think you'll be able to do this, replicate this with other tables, other situations. So what we're going to do is we're going to look at the differences, like the first order differences and the second order differences. And remember that the first order differences, they are Well, they're going to give us the average rates of change if the x's are spaced out by 1, which they are in this case. But if they're not spaced out by 1, it won't give us exactly the average rate of change, but it will tell us the sign of the average rate of change, which is what's going to be important here. Whether it's increasing or decreasing, that would be where the average rate of change was positive or negative. And so we're going to jump in and do that right now. Okay, so first I'll say 4 to 3 is -1, and 3 to 1, that's a difference of 2. Okay, so these is like related to the rate of change, not necessarily average. It is in this case, but not in general. And then if we look at the second order difference, -1 to -2, well, that's a subtraction of 1. That will tell us how the rates of change are changing, right? The rate of change decreased from -1 to -2. So I'm going to say, well, if the rate of change is negative, well, that means our function's decreasing. And as a result, I can get rid of these two answer choices. Any of these that have to do with f increasing, those are out now. And also you can see that the table has x increased from -1 to 1, f decreased. Okay, and then we're looking at the rate of change of the rate of change, and that's a negative number 2, and that's telling me that the rate of change is decreasing. And as we know now, that means that the function's graph is concave down. All right, so we're looking for decreasing and concave down. That's answer choice D. That's something that we could do. Right. Okay, and then the last example I've got is got another table. It's up above, and it's a little more diverse. We got some information about the rate of change on varying intervals, and so let's just jump right into it. I'm going to start with the question and then let the question guide my analysis of the table, which I think is different from how I'm going to be working it on the homework, but that's a different consideration. So f is going to be increasing when its rate of change is positive, and f will be decreasing when its rate of change is negative. So I'm going to go in and I'm just going to look for that in the table. I'm going to say, all right, rate of change is positive here and there. Okay, so I'm going to say, all right, that means from 1 to 2, just like it told me, and 3 to 4. And for rate of change, or for decreasing, f is decreasing when its rate of change is negative. Can't emphasize that enough. That's going to be here and there. So that would be 2 to 3 and 4 to 5. Right. Find the intervals on which f is concave up / concave down. So I just have to remember the definition of concave up and concave down in terms of the rate of change. Concave up is rate of change increasing, and concave down is rate of change decreasing. And we'll just go and look for that in the table. Rate of change is increasing, that'll be here and there. And just those two. So from 1 to 2 and 2 to 3, I mean, we get to say 1 to 3. I think that would be all right. So 1 is less than x and is less than 3. And the rate of change is decreasing pretty much everywhere else. So let's say right here and there. And that's going to be where x is greater than 3. Or, from 3 to 5 if there's a limited domain on this function. Right, and so that's how we're going to determine concavity based on this table of information about the rate of change of f. Okay, where does the graph of f have a point of inflection? I think now would be a good time to remind you that a point of inflection is a place where the concavity changes. So change in concavity. Okay, and what we said that concave up was from 1 to 3 and concave down was from 3 to 5. So that means that at x equals 3, there was a change in concavity. Okay. When is f both decreasing and concave up? Okay, so this is kind of a backwards translation. We're looking to what does this mean in terms of rate of change? And that's actually how I'm going to end the videos, with us filling out a grid, just to really reinforce it, hopefully. But decreasing and concave up, decreasing is when the rate of change is negative. So we're looking for in the table where the rate is negative and decreasing. Or, pardon me, I wrote decreasing, I meant to write increasing. Concave up is not a decreasing rate. Okay, pardon me. But here I am so deep into the video, definitely not worth re-recording, right? So I'm going to say that's increasing, and obviously beg for your forgiveness, and look to see where I see blue and green in the table, and I was up here, that's from 2 to 3. All right, so f is both decreasing and concave up when x is between 2 and 3. Alright, so that's all the examples we've got. In this lesson, we continued our analysis of rates of change. We defined local maximum and minimum, concave up and concave down, and point of inflection. We answered a bunch of questions about functions and their rates of change based on graphs and tables of data. Okay, we covered parts of topics 1.4 and 1.1 from the AP Pre-Cal course description. And since you stuck with me this long, I think I'm going to help you make something that would be actually really useful for you as you work on the homework here. Alright, so I've got this grid here, and if you want a copy of the grid, I'm sure there's a link in the description to a place where you can get this grid, or, if you're in my class, you can just come see me and I'll have a bunch of them printed out, or you can make one on your own. I don't think it would be too hard to make one of these on a sheet of paper. Okay, what we're going to do is we're going to go in, increasing, decreasing, concave up, concave down, maximum, minimum, point of inflection, and kind of describe them in terms of the graph of the function and the rate of change, which would be like kind of the more wordy explanation. This is a different version of a grid that we make in my calculus class. Okay, so the graph of f is increasing when it's going uphill as I move left to right. Say the decreasing is where as I move left to right, the graph is going downhill. Okay, the rate of change from an increasing function is positive, and the rate of change of a decreasing function is negative. Concave up and concave down, those are kind of like the attitudes of the graph. Are they happy or are they sad? So a graph that's concave up is smiling. Okay. Now, I always like to draw two pieces of graph, with the eyes. I like to draw one that's increasing and one that's decreasing, both that are concave up, just to remind myself that concave up doesn't have anything to do with increase or decrease. Function can be increasing in concave up, it can be decreasing in concave up. It's all the same. What it means in terms of the rates of change is that the rate of change is increasing. And on the other hand, concave down is where the graph is frowning and where the rates of change are decreasing. Okay, a maximum, something like this, place where the graph goes from increasing to decreasing. What we would say in terms of the rate of change is that the rate of change went from positive to negative. I was about to say it, but the rate of change went from positive to negative. And in the same way, a local minimum or relative minimum, that's just where the function's graph changes from decreasing to increasing, or where its rate of change went from negative to positive. Okay? And a point of inflection is a change in concavity. That's important to remember, because that's not super obvious from the words. Okay, these can kind of come in a variety of forms. They could look like something like this. Okay, went from smiling to frowning. It could go from frowning to smiling. I think that's actually kind of a more familiar point of inflection from Algebra 2. And then it could do something like really weird, like frowning and then suddenly start smiling, but also reverse its direction. That's a point of inflection too. Our definition of concave up and concave down in terms of rates of change were increasing and decreasing, so a change in concavity would be a change in the rate from either increasing to decreasing or decreasing to increasing. Okay, and I think that's where I'm going to leave you. It's almost 40 minutes, almost twice as long as I'd like these lessons to be, but this one might be twice as dense as usual. Okay, and I recognize that this is, it's a little more challenging than usual, and this is going to be a little more thoughtful and less solving, but I really think that with enough practice, you'll be just fine with this. And this is the type of topic that we will continue to revisit as we get, new function types throughout the year. So I guess that's going to be all for this video. Thanks for watching.